Hello and welcome to another video. This is actually going to be a long one, I believe. There are a bunch of things that need to be discussed, and I hope I don't lose you throughout at any part of this video. But in case there's anything that's confusing, please feel free to drop a comment, and I'll address that. But in this video, I want to talk about a bunch of things. So first up, we want to understand how negative binary numbers are represented. And of course, as we can see, the register values are displayed in hex, so in hexadecimals. So we will want to see how negative binary numbers are then shown here. So we'll take a small example. In fact, if you see instruction 5, I'm moving -7 in R0, so we'll see what -7 looks like, and we'll deconstruct it to understand how we can basically represent -7 in binary and then in hexadecimal. So that's the first thing. Then we're going to talk about the logical shift instruction, right? So LSR, logical shift right. We also want to see arithmetic shift right. And then toward the end, we want to understand when to use which one. What's the difference? They're both shifting, but what does it mean to logically shift and arithmetically shift? And what does it really mean? When do we use which one? So let's begin right away. I've got this bunch of code. I want to go ahead and step one by one. I'm already in the debugger mode, so let's go ahead and do it. Move -7 into R0. When you move -7 into R0 register, you see this value set up. You see these Fs, and then there's a 9. So -7 is being represented as 9, and then there are all Fs before it. Why does this happen? So let's try and break this down and understand this by looking at its binary representation. So to represent -7, one of the ways to do this is to see what +7 looks like in binary. It looks like this: 0, 1, 1, 1, right? 1, 2, and 4. These three bits get turned on: 4 plus 2 plus 1, 7, and that's how +7 is represented. To represent -7, now we take a 2's complement, which means we invert these bits first. 0 becomes 1, all 1's become 0, and after we have inverted them, we add 1 to the least significant bit, right? So this then completes our 2's complement, and this is the representation for -7. But since the register values are in hex, so what that means is, um, and it's okay in this case, but if the number was 10, then we would have A, 11, then we would have B, all the way till F. But here we're looking at 4 bits together, and these make up as 9 in binary, right? As an unsigned number. So we consider these hex values as unsigned numbers. So that is why we see 9 as a representation of -7, right? So we move -7, the register shows 9, but why do we have all F's before it, right? So these 28 bits, these 4 bits constitute one hexadecimal alphabet. So what are these 7 F's or these 28 bits? Why are these F's, right? Which means why are these ones? Remember what 2's complement does. Uh, we are inverting these bits, right? So you expect that a +7 had all zeros before it, and when you took the 1's complement, you inverted all those bits to 1. Then for the 2's complement, you just added 1 to the least significant bit. But the previous 28 bits remained as 1's, right? And when you represent those 1's into hex, they would show up as F's, right? So that is why you have these F's showing up and then 9. We have specifically seen why this is 9. So the -7 is then represented as 9. So that's the first part. That's the representation of -7. You are encouraged to look into other representations, try changing this number to different decimal and negative decimal numbers, see what you get in binary, practice on your own, and make sure it aligns with your understanding in hexadecimal for these register values. Now, let's move on and get into the next part of this, which is understanding what logical shift does, right? So for that, I'm going to use this as an example. I'm going to move 8 into R1, and let me go ahead and do that. I have 8 in R1. It's fairly straightforward. Uh, Now I'm going to go ahead and execute logical shift right. So LSR is logical shift right. And the convention here is very intuitive because this is similar to other instructions also. You have the destination register first up, then you specify which register or which data are you trying to logically shift, and then you specify the amount of shift. Okay, so if I break this down one more time, the destination register, where do I store the results? What's the destination? That's R2. So we'll be seeing our results in R2 after logically shifting the value in R1. So R1 had 8 stored in it. We can see it. We will logically shift it by 2 and store the result in R2. But what does it mean to logically shift it? Let's go ahead and execute this. The answer is 2, right? So 8 has become 2 after a logical shift right of 2 bits. So what does it mean? Let's deconstruct this and understand what logical shift right means here. So notice this is what's happening. You represent 8. This was our original number, which in binary is 1, 0, 0, and 0. And logical shift right is quite literally shifting this bit, all the bits actually, to the right hand side. But since these are zeros, we don't see that shift, but we see the shift for 1. So it's shifted 1 bit and then the second bit. And that's how we see this one being shifted to here. It has shifted 2 places. So it has shifted 2 bits, right? And that one is being shown here. This, and notice how zeros get filled in from the left hand side. So this then is in binary a 2, right? Um, this is how 8 has become 2. Notice one more time. 8 in R1 after logical shift right of 2 bits has become 2 and it's stored in R2, right? So shifting this to the right hand side because it's logical shift to the right R, right? So shifting 2 bits to the right is quite literally shifting the bits to the right hand side, and we get a resultant number. We can convert it into decimals. But if you look at it from a mathematical perspective, what's really happened is when you're moving to the right hand side on bits, you are essentially dividing the original number in powers of 2. And the power is specifically the amount of shift that you have specified. So you have specified a shift of 2. This means you're dividing your original number by 2 to the power of shift, which is 2 in this case. 2 to the power of 2 is 4. So 8 is being divided by 4, and the answer is 2. Now, let's reaffirm this understanding by changing the shift. So here in instruction 8, we're doing the same thing. We are logically shifting right R1, the same value 8, but this time we're shifting it by 3 bits, and we're storing the result in R3. So let's go ahead and do that and see what do we get. So we get 1 this time. How has 8 become 1 after 3, after shift of 3 bits to the right hand side, right? So let's understand why this happens. Let's have a look at this. There's your 8. That's the 1 bit. 1, 2, and 3. So 3 bits to the right hand side, 3 shifts to the right hand side will give you 1, right? But that's quite on the bit level. But mathematically also, it's being divided by 2 to the power of 3, right? And that's the shift this time. The shift is 3. So 2 to the power of 3 is 8. 8 divided by 8 gives you 1. Now, intuitively, you could come to the conclusion that because we're shifting these bits to the right hand side, it means we are dividing by this number. A logical shift left is actually going to do the opposite of division. It's going to multiply the original number, right? So a logical shift right is dividing our original number in powers of 2, depending on what the shift is, and a logical shift left is going to multiply our original number. So that is just by intuitive understanding of this. Now, we've understood what logical shift right does. Let's move on to the next aspect, which is the arithmetic shift right. So ASR, that's the code. ASR, that's the instruction, ASR, and it follows the same convention. You specify a destination register, you specify a register that you want to shift, and then you specify the shift amount. Okay, so this is something we're going to do. Let's execute this, and what do we see in R4? We see 2 being stored here. Notice this is quite similar to what we did with logical shift right. Again, we're still working on the number 8. That's what's in R1 in arithmetic. And let me also execute instruction 10, because it's the same instruction, arithmetic shift right, only the shift has changed from 2 to 3. This is the same thing that we did with logical shift. We changed the shift from 2 to 3. The results changed from 2 to 1. Here also we're going to see the results changing from 2 to 1. So basically we're getting the same results that we obtained with logical shift. So then the question here is, if logical shift right is shifting 2 bits to the right hand side, arithmetic shift right is also shifting 2 bits to the right hand side, and it's also dividing the number by powers of 2 depending on the shift, where is the difference then? So there is a subtle difference that needs to be understood, and we're going to get right into it. But for our example so far, we've seen that for positive 8, there's been no difference. Think you get the same results. But where you really do get a difference is when you come across signed numbers. Okay, when you come across a number such as -8, for example. So let's go ahead and move -8. We've moved -8 into R6. This is what -8 in R6 looks like. And then let's understand what if we get the same or different answers, right, for logical shift right and arithmetic shift right. Before we do that, we also need to recall our understanding of representing negative numbers. Notice just because it's -8 and you see an 8, that's not the reason why an 8 is there. And then there are all f's. Let's break this down. Let's see why we have a -8 over there. It just so happens that for a 8, for it to represent a -8, you look at the representation of positive 8, and it's 1 0 0 0. You invert the bits, and then you add 1, and the carries go over for the binary addition, and you end up in the same original uh, representation of positive 8. So it just so happens in this case that for -8 and positive 8 you have the same representation. So that is why you're seeing an 8 here for a -8 representation. But there's a difference between a positive 8 and a -8. You see all these f's behind this 8. Again, all of these f's are there because when the positive representation, notice there were all zeros behind this, and to represent it in negative, those zeros got inverted and they became ones, and in hex that would be represented as f's. So that is why you have 28 bits of 1, meaning 7 digits of hexadecimal as f. So that's why we have 7 f's, and then there's an 8. But that's about representing a negative number. Let's try to understand what is the difference in shifting bits of the negative numbers for logical shift right and arithmetic shift right, and what answers do we get actually. So remember, for the positive case, we divided 8 by 2 to the power of 2, meaning we divided 8 by 4 and we obtained an answer of 2. So we are expecting answers of, you divide -8 by 2 to the power of 2, and that's 4. Divide -8 by 4, you should be expecting -2. So let's see if we get -2, or which one of these will give us -2, and what do we actually get, and what's really happening. Let's dive right into it. I'm going to go ahead and execute both of them. So R7 gives me this. This is a 3, and then there's 6F, and then there's an E, and that's the logical shift right, R7. R8 has the results for arithmetic shift right. Now, the arithmetic shift right has all F's, and then there's an E. First off, let's try to make some sense out of why we are getting an E it has something to do with the bits being shifted. And then let's try to understand why we have 3 and F. Okay, for the most significant bit in R7 and R8 for logical shift right and arithmetic shift right. So, of course, we started with -8 and we were shifting this to the right hand side for 2 bits. So you expect this 1 to be shifted 1 and 2. So you expect this 1 to be here. Let's have a better representation of this. Here, I'm going to use this to get an understanding of this. Yeah, so this is -8. This is the original number. And you see this 1 being shifted twice here. And once you do this, notice you're shifting all the bits to the right hand side. So these two ones also get shifted here, and together these 4 bits construct one hex number, which in this case is E, which is why we see E, right? The 1 is not turned on, 2, 4, and 8 are turned on, so 8 plus 4 is 12, plus 2 is 14, and 14 in hex is E, right? So this is why we see E. And this is the same for logical shift right and arithmetic shift right. Because the bits get shifted to the right hand side, the 1 is going to be here. The 1 is actually going to be here. But then, uh, actually, this should be 1 0 0 0. Let me very quickly uh, fix this if I can. Because notice this is -8. It's 1 0 0 0. And this is -8. So this should also be 1 0 0 0. We'll very quickly fix this up. 1 0 0 0. Okay. Yeah. So these are the same numbers, right? We started with -8 for both. So -8 for logical shift right. This one got shifted twice to the right hand side. So we have this one here, but these two also got joined in because they got shifted here. Same idea for this case also. We'll just change this color to white. Okay, same idea because it's -8 here too, and then this gets shifted twice here, and then these two also get shown up here. So that's still an E. And we have E's for both cases, for R7, R8, for logical shift and arithmetic shift, R7, R8, they both have E's. So that's how E's make sense, right? One gets shifted twice, previous two ones get shifted here, together they make a hexadecimal number, 14, is represented as E. So that's the same idea for shifting in both cases. But what's really different is what happens at the most significant bit uh, in that specific part. Notice for logical shifts, zeros get filled in as the entire number gets shifted to the right. But for arithmetic shift, ones get filled in as the number moves or shifts to the right hand side. And because these ones fill in, they together make an F, right? Which is 15 in decimal, which is why you see for arithmetic shift R8, you see this most significant bit, hexadecimal bit here as F. That is why you have an F over here. But when you plug in zeros, which is the case in logical shift, this results in 3. The question then is, which one is the correct representation? Now, I leave it to you to find out what this number 3, 6 F's and E make up, but we know for sure all F's and E, this is in fact a representation of a -2. In fact, you're encouraged to try this also. Try to see how you can represent -2 in negative binary, right? So you will come across exact same representation. And this tells us that when you have -8 and you are shifting 2 bits to the right hand side, meaning you're dividing it by 2 to the power 2, which is 4. So -8 divided by 4 should give you -2, which is what we get. Now then the conclusion here is that for negative binary numbers, it is arithmetic shift right which works perfectly and you see the expected behavior. But when you have unsigned numbers or positive numbers, both give the correct or the same answers. This is exactly what we saw here. For plus 8, R2, R3, we varied the amounts of shift for logical shift, right? R2, R3, they gave the same answers as arithmetic shifts. R4 and R5, 2 and 1, 2 and 1, 2 and 1, right? Shift by 2, shift by 3, shift by 2, shift by 3. So they respect the shifts. They divide as they should in powers of 2, depending on the number of shifts that we place. And the expected behavior is consistent between the two of them, but for positive numbers, right? Positive binary numbers. For a negative binary numbers, it is only the arithmetic shift right which functions correctly in the expected way. Logical shift right does not do it, and that is because the logical shifts to the right bring in, they fill in with zeros, and that changes the number in itself. I hope this makes sense and this is clear. Again, 4 ideas: representation of negative numbers. That's what we started with. Understood what logical shift right means, understood what the arithmetic shift right means, and then we tried to understand why there's a difference between the two and when does that difference become evident. And if you saw, it becomes evident when we represent negative numbers or we shift negative numbers. So I hope this makes sense. And in case there are any questions, I'm happy to address them in the comment section. Until next one, thank you.